Institute. The speaker of today is Giel Ramaekers from University Eindhoven, and about iron powder, combustion, and more. We will hear about that. So I know Giel for a long time. He attended my lecture in Delft, and I was member in his PhD thesis committee. And in fact, I can already mention that this thesis is still useful for many people because it's on flame-net-generated manifolds. And if you were wondering about some equations and so on, how is it precisely, you can go to that thesis, and in many cases you find answer to your question. But then Giel went into software engineering for combustion-related projects outside academia. And only recently he returned to academia, and so he is now in a very good position to combine all that in his most recent projects at Eindhoven University. So let's say here we have a scientist with a very wide experience. So from mathematics to industrial applications. So Giel, the floor is yours.
Thank you very much, Dirk. Thank you very much for this very nice introduction. You're too kind. First of all, can everybody hear me well?
Yes. I think so.
Yeah. So I will take this this lecture to introduce you in the world of iron powder as a cyclic energy carrier. It will be we will touch several subjects, and I would like to mention first of all, I am part of this research group, and I will show work of all of our colleagues. So it's my part is only a very small part, and it's I take pride in being able to show all of my colleagues' work. So first of all, let's start with the current transition towards sustainable energy and the difficulties that arise from that transition. Is that, of course, we would like to get rid of fossil fuels. We would like to get rid of the CO2 production, causing, of course, the greenhouse gas effect. But this is not that easy. The main two renewable sustainable energy sources we are developing at the moment, wind and solar, they have a huge discrepancy between, well, when we can harvest them and when we need them. So there is a daily imbalance, the day and night, but also a seasonal imbalance. And they are variable. We cannot really count on them. If it's a cloudy day or there is no wind, then we cannot harvest these sources. So what we would like is to be able to store these energy sources in a safe way. And at the same time, this is not an unimportant issue as well. There has been developed quite an expensive infrastructure in the last years, decades, which we would like to reuse, at least partly, as much as possible. Think of the coal power plants. The most recent one have been commissioned just years ago, and they have a lifetime of 40 to 50 years. And if we would abandon these, that would mean a huge economic loss. So we would also be very interested in reusing this existing infrastructure. Then how do we come to the metal powders? So the metal powders as energy carriers, which is the subject of this talk. So this sustainable energy we would like to store, can be stored in various ways. Of course, the batteries, they have gained enormous attention over the last few years. But if we look at them, they would be located very in the lower left corner of this graph. They have a very small and
Giel, we cannot hear you.
Same thing goes for ammonia or formic acid. They are quite toxic. which leaves metals. And if we then take a look at metals as a group, then we see that they have approximately the same volumetric energy density as hydrocarbons we are used to. But the energy density, so the gravimetric, is somewhat lower. So meaning per volume of iron powder, you can extract approximately the same amount of energy as you could from the same volume of hydrocarbon, but this volume is significantly heavier. So that also kind of implies that these fuels, they are very interesting for so high power density applications, which are stationary, so that you don't have to move this heavy fuel. If we take the selection of the most suitable candidates, so we remove, for example, lithium, which is very reactive with water. We remove beryllium, which is beryllium oxide is highly toxic. So then we have a selection of the most feasible candidates. And if we take a close look at how they burn, then Jeff Berg-Thorsen distinguished 3 ways of burning these metal particles. The first of all, mode A means that the metal first has to vaporize and then burns in a halo. Mode B means that the metal does not boil. It remains below its boiling temperature, but it does produce significant amount of metal suboxides. And then mode C, which is the most favorable mode, is a particle which simply absorbs oxygen, but stays in a condensed phase and does emit a very limited amount of metal oxides. And if we make so thermodynamic equilibrium calculations for these most suitable candidates, we see that only iron does not boil. So the metal does not boil at its adiabatic flame temperature. So it remains in condensed phase, liquid phase. And during this combustion process, it also does not emit significant amount of iron oxides. So it does emit some, but this is a very negligible amount, especially compared to the other candidates. And this makes iron the most suitable candidate to our opinion, especially since these either these gaseous oxides or gaseous metals, this is something we do not want. We want to use this as a recyclable fuel, so in a closed loop cycle, which we'll get to. So we should not lose either metal or metal oxides. We should be able to recapture all of it, ideally. So iron, to summarize, is a safe fuel. It's non-toxic. It has all the potential to be good, so to be very recyclable. Of course, it is cheap. And as we've seen, it's quite compact. So comparable to the hydrocarbon fuels we all know. So that leaves us with iron. So then how would such a cycle look? I think most of you have seen this picture before, so I'll go through this quite quickly. So on the left, we have renewable sources, solar and wind typically, which produce green electricity. This green electricity is used to make hydrogen, and hydrogen and then is used to reduce the burnt fuel. So this, in the middle, you'll see a reduction oxidation cycle, in which on the left, first of all, fuel is created by reducing the burnt powder. And when there is a demand for power, this renewed fuel is then burned in the combustor, and the products are captured to be reduced when there is an excess of green electricity again. Then during this combustion process, we can extract heat to drive industrial processes or electricity production for domestic use, for example. And the sentence below is, let's say, a bold science fiction suggestion, is that if we would like to get rid of coal as a fuel, then of course we have a couple of quite new coal-fired power plants. They are near shore. So near shore means close to offshore solar and wind producing regions. And if we could retrofit these coal-fired power plants to be used with iron powder as an energy carrier, then we could reuse a large portion of the infrastructure and also get rid of the CO2 emitting coal as a fuel. So then, of course, how do these powders look like? We're talking about powders as a generic thing, but if we looked at it in more detail, then we see first of all that no two powders are equal. So these, I have pictures of unburned particles here, but these powders, they are blends of particles having a range in diameters. So it's not a monodisperse powder as you would ideally have. It's a blend of multiple diameters. And as we see, also the morphology of the particles is quite, well, varies quite a lot, even within a batch. So this is in terms of specific surface, porosity, these differ quite a lot. Then, which is less visible, sometimes these particles also have minor impurities, and these impurities can have an effect on either the combustion process or the reduction process. So they should be characterized as well. So this is how they would look as fresh powders. So this is what you would buy. But then, of course, we would go through this cyclic process of oxidation and combustion. So on the full left, you will see the powder as that would be bought the first time. This is quite irregularly shaped. We see a range of particle diameters. And then after combustion, this is not exactly the same powder, it's just as an illustration. We see more spherical particles, first of all. And this is because these particles, they burn and become liquid during this combustion process. And the surface tension, at least that is the hypothesis, make sure that the particles become spherical then. So this explains the spherical shape of the particles. We also see some holes and exploded particles as well. This is something we do not understand fully yet, but there is an hypothesis that these particles can absorb more gas than the structure can withhold during cooling down. And then it needs to expel gas, most likely oxygen, during the cooling down phase, and the particles, they crack or explode, or they open up at least. So this is the hypothesis, the most likely hypothesis for these exploded particles. So then we have burnt the particles, we capture them, and we reduce them in the second step to be able to reuse them again. So, and the picture on the right shows how these particles typically look after reduction. So you can see porous sponge-like particles in which the oxygen has been extracted from the particles and leaves, let's say, a sponge-like matrix of iron again. And this porosity can be affected by the conditions under which the reduction process takes place. So this is current work of Konrad Hessels. And then we go back to the picture in the middle again. So an important thing to notice here is that the fresh powder pictured on the left is most likely something not that important to characterize. What is important is to characterize the porous material on the right, because this is the powder that will be used over and over and over in the subsequent loops. The powder on the left will only be used once in the initial loop, and after that one, it will be the porous material for loop 2, 3, and subsequently. We of course want to scale up. This is not just kilowatt scale. We would really like to move towards these the same power scale as the coal-fired power plants. So in our university, in our department, so we are conducting a wide range of experiments running from single particle combustion, pictured completely on the left, to let's say small flames and kilowatt scale flames, so the tornado burner. And in Metalot, there's even a 100 kilowatt proof of concept. So the MP100, which is currently being retrofitted to run on 200 up to 500 kilowatt of thermal power. So with these images, I would like to show that is important, first of all, to understand what is going on a single particle scale, because there are very many open questions on what is actually happening within such a particle during combustion, but also how do these particles behave in large aerosol clouds. So then we're talking about the tornado burner and even the MP100. If we zoom in on the first experiment, so this is a quite recent experiment conducted by Daguan Ning. Daguan Ning, he built an apparatus which releases a stream of single particles. So this is pictured on the top left, in a shrouded flow. So he can control the release of the particles. So they are released individually and they are covered by a shrouded flow of which the composition can be controlled accurately. So once these particles leave the apparatus, they are hit by a laser, showed in the lower left, and the particles, they are ignited by this. They're rapidly heated up to approximately 1500 Kelvin, which ignites them, and then they burn. And the process is then captured by optical equipment, and the temperature profile of such a particle is then shown on the lower right. What we see first, the particle is ignited, then it ignites, it burns up to the time of maximum temperature indicated by Tmax, and then it cools down until T total. So the two important, so there are several important factors, but two of the most important ones is the maximum temperature, of course, how hot do these particles get, but also how long does it take for these particles to reach this maximum temperature, so time to maximum temperature. So the important findings, and I just selected three major ones here, is that combustion peak temperature, so the maximum temperature that particles attain during this combustion process, depends on particle size and oxygen concentration of this shroud flow, of the encapsulating flow. And typically, larger particles, they reach higher maximum temperatures. Another very interesting finding is that the time to this maximum temperature scales approximately to d to the power 1.5 approximately, which is quite close to the analytical d squared law, which can be deduced for droplet combustion, so vaporizing droplets which combust, implying that if a particle has twice the diameter of a reference particle, it will take 3 to 4 times as much time to burn. And this was quite nicely defined for several conditions, so several oxygen concentrations. The last important finding I would like to highlight here is that there seems to be a nearly linear inverse relation between the combustion time to Tmax and the oxygen concentration in this oxygen nitrogen blend. So meaning if I double the oxygen concentration, I would halve the time to reach the maximum temperature. Right. Next step is, of course, if we can use these, so the experiments have been conducted, we have a large, very interesting data set. Next step would be if we can use this data set to derive a model which can actually also predict combustion behavior in other conditions. So the basics, so the fundamental, the backbone of this model is described here. And the most important equation, I guess, is the second one, the mass transfer. So it is assumed here that a particle absorbs oxygen. So it increases its mass by absorption of oxygen, and then this oxygen is used to convert iron to iron oxides. And then the assumption here is that there is a balance between the amount of oxygen which is adsorbed and the oxygen that is used for this oxidation process. So in other words, there is no oxygen stored somewhere. All oxygen that is adsorbed is also used to oxidize iron to iron oxides. If we apply just a minor amount of mathematics, we can extract the mass fraction of oxygen at the surface of the particle, and we get this the expression for the change of mass of the particle as a function of the normalized Darmkeulen number. And this normalized Darmkeulen number is an indication of what process is dominant. So there are two extreme cases, two limiting regimes. And first of all, the kinetic limiting regime. So kinetics are very slow. This is typically true for cold particles. So the particle has access to enough oxygen, but simply the kinetics are not fast enough to convert, to use all this oxygen to convert iron to its oxides. So this is typically true for the initial phases where the particle is still cold, or the very late oxidation processes to so to hematite, so the last oxides in the chain. The other limiting regime is the diffusion limiting regime. So this means that the diffusion is slower than kinetics. In other words, kinetics are really fast, particles really hot. So the kinetics can just use all the oxygen that is available to convert iron to its oxides. Diffusion can simply not supply enough oxygen to let these kinetics run as they want. So the conversion process is really limited by the amount of oxygen that is transferred towards the particle. And this is typically true for hot particles. So then the kinetics are really fast, but simply the diffusion process cannot supply enough oxygen to further speed up the process. This is just a small part of the model, the models we have been deriving. So, but this is the most important backbone, and to distinguish these two limits is something which is important to keep in the back of your mind. Models we have been developing, and I'll get to these specific models later on, also contain much more detailed ingredients. So we have detailed heat transfer for particles containing both convective and radiative heat transfer, and of course heat release by means of the oxidation process. Then it accounts for slip velocity. So the particles, they have a certain slip velocity. They're quite heavy. The density is much higher than air, so they have a slip velocity with respect to the carrier gas. They absorb quite significant amounts of oxygen. So there is the flow towards the particle, Stefan flow, and this will cause for a correction in typical correlations. Then we use detailed gas phase properties, both thermodynamic and transport properties. And also for the solid phase, we have composed quite a database containing temperature-dependent properties. And I've just shown density and enthalpy here for iron, but we have these for several oxides, and we use them in the simulations. If we then use this model to reproduce the experiments by Daguan, then we need to notice that, of course, Daguan, he measured a number of particles, and these particles, they come from a particle size distribution. So we feed the same particle size distribution displayed in the top left as Daguan has measured or used to do his experiments. So we feed the same particle size distribution to the simulation. Same thing goes for the initial temperature. These particles are perhaps not hit directly in the middle by the laser beam, causing them to be slightly cooler. Also, smaller particles which are hit completely by the laser beam will be slightly higher than bigger particles. So for this, to mimic this, we assumed a normal distribution in the initial temperature of particles. And then we leave all these particles and we follow them in time. resulting in the gray arrow band in the top right graph, where the black line is the reference particle, so it's the mean particle diameter. But it's important to notice here that we can reproduce the experiments by Daguan quite accurately. We can get the same trend, we can get the same maximum temperature approximately, and the time to maximum temperature can also be quite well be reproduced. And this is a simple unresolved model only. Interesting to see here is the plateaus, of course. First, there is a plateau at approximately 5 milliseconds where the iron melts. This is it's already oxidizing, but this is melting. Then it burns approximately until 25 milliseconds, cooling down phase, and so between 37 and 42 milliseconds, we see a solidification of the FeO oxide, which is the only oxide present in this simulation. And then recall this normalized Darmkeuler number. If we plot this one, then during nearly the entire combustion process, so from 0 to about 27 milliseconds, we see that this normalized Darmkeuler number has the value unity, meaning that this is a completely diffusion limited oxidation process. Kinetics are really fast, particles really hot, but it is limited by the amount of oxygen that is transported towards the particle. Then another PhD student from our group, Leon Thijs, he took these single particle simulations to a next level. So the previous slide showed results from an unresolved model. Leon built a model using a resolved single particle model. So that's displayed on the left. He really resolved the gas phase, including the entire boundary layer, on a single particle. So we don't have to use several correlations to predict mass transfer to the particle. This can all be now simply be resolved in the model from Leon. And what I would like to show is that the predictions of this time to maximum temperature are very well captured by this model. So for a range in oxygen concentrations, we can capture the time it takes to reach maximum temperature. And also the maximum temperature itself, so displayed on the right, was quite well captured by this model. And for this picture on the right, it needs to be noted here that so these particles, they get really hot. Radiative heat transfer is very likely to be important, significant, or even very important. And this is exactly one of the parameters which contains still quite some uncertainty. So the discrepancy between experiments and numerical simulations here, to my opinion, is very good. So it's they are very much alike, considering the very high uncertainty we have in certain properties which need to be modeled. So we were quite pleased with these predictions. And Leon took it even further, because in the movie, this is a movie by Daguan, we can see a single particle leaving the injector, burning. And if you look well, then you see a cloud formed. Now, this is a grayish cloud. And this was an observation made by Daguan, which are most likely gaseous oxides or nanoparticles leaving the particle. So the particle is very hot, and a small amount of iron or iron oxide evaporates and creates a cloud of these iron oxides and nanoparticles. And Leon included the sectional model to try to mimic this. And in the middle, you can see an instantaneous snapshot between luminosity measured in the experiment and nanoparticle concentration in the simulation. And of course, it's a qualitative comparison, but it seems, so Leon found quite a good agreement between his predictions for nanoparticle formation and luminosity measurements made by Daguan. It is important to notice here that the amount of iron that evaporates is very minor. So the graph on the right shows that we're only talking about order of magnitude 1%. So we only lose a very minor amount of iron, and this is already for an extreme experiment where the particles are ignited by a laser up to an initial temperature of 1500 Kelvin. So this is already quite an extreme case, and then still we only lose a very minor amount of iron. And this is more or less also, this substantiates the graph on one of the initial slides where we show that iron produces a very minor amount of gaseous suboxides, making it the most suitable candidate. So the next step, of course, if we take it from single particles to one-dimensional flames, then we come to the work by Thijs Haasberg and Toos van Gol. The next step is to be able to predict quasi one-dimensional laminar flames. So for this purpose, we extended Chem1D. I think most of you will be quite familiar with Chem1D. Thijs extended it with a Lagrangian model to model the particle, discrete particles. It's a fully two-way coupled solver. So the volume of the particles is approximately 1e minus 4. So that would be a dilute particle-laden flow. Slip velocity between particles and carrier gas is accounted for, as well as Stefan flow. And we use detailed gas properties again, and temperature-dependent properties for the iron particles. And the purpose of this goal is to make the step from single particle oxidation towards flame propagation in iron clouds. So we would like to predict how fast, so what would be the flame speed or percolation wave speed in these iron aerosol clouds. There is an important thing to notice about this code. So it's a kind of a hybrid approach of continuous. So we use a steady state assumption for the continuous phase, and we track the particles as they move through this continuous phase. So we assume that this metalet, so one-dimensional iron aerosol flame, is in steady state. It does not capture discrete effects. It does not capture stationary effects or igniting particles. It assumes a homogeneous, continuous regime. So it assumes that the flame, so the percolation wave, really moves as a continuous through a continuous aerosol. The last major extension has been made by Toos van Gol, because one of the limitations of the initial implementation is that it can only account for oxidation to the first oxide, being FeO, and not to the second and the third one, being magnetite and hematite, containing more and more oxygen. So this Toos showed that this is a good approach if you have a very iron-rich flame, so an excess of iron. In that case, all oxygen is consumed quite rapidly, and only FeO can be formed. There is no excess oxygen that can be used to oxidate to higher states, so magnetite or hematite. And in this case, her extended model reproduced the previous results quite well. If we then take a look at a case where there is an excess of oxygen, so that's the right graph, the model made by Toos could predict the production of higher oxides, being magnetite and in another case also hematite. And this is important. This is something the initial model could not do because it stopped at FeO. But in experiments, we do see that magnetite and hematite are formed. So if we have experiments and we analyze the burnt powder under conditions of excess air, combustion conditions of excess air, we do measure quite significant amounts of these two oxides, so Fe3O4 and Fe2O3, making it necessary to to extend our modeling capacity to incorporate these, to include these two oxides. So this is work in progress and will be submitted soon, but it has been a large step forward in also capturing these higher oxides. If we then make another step, well, I would say upward in scale. So we lose detail, but we will be able to capture larger scale flames. This OpenFOAM implementation has been made in our group. It has been validated extensively also using so homogeneous flames. For these methane air flames, quickly shown on the left, we could really reproduce results predicted by other codes, being Cantera and Camodi pretty well, as well as experimental results, giving us faith in the implementation of the code. It uses the same discrete particle model, which has been validated on the experiments from Dagwan. And this is now a quasi 1D flame. You see a tube filled with unburned particles. Blue means iron only, no FeO yet. And as I start the movie, you'll see a flame front. So move towards, so through this tube. So it only depicts the burned particles having an FeO content of 0.7 or higher. And you see this percolation wave move through the iron aerosol cloud. And with the displacement of the flame, of course, of this percolation wave, we can predict, or we can extract the flame speed. And of course, this depends on either the particle size distribution, the particle loading of the flow, how much particles, how much iron there is, can also be interpreted as the equivalence ratio. So this is the a 1D flame moving through such an aerosol cloud. Next slide. There are not many experiments made which can be used to validate these large-scale codes, but one of these experiments is a rather old one made by Sun, which is an aerosol cloud which is ignited in the middle, and you have this spherically expanding flame. And then what we would like to extract is the speed of this percolation wave. So the velocity with which this spherical flame expands. And we would like to compare that. So the experiments to predictions we've made and how this looks. So it's ignited in the middle. This is the temperature shown on the left. And you see it's like a spherical flame in a box, which expands. And the percolation wavefront is perhaps better illustrated by the velocity at which it's traveling. And this is the major thing we would like to extract from these simulations. Can we actually capture how fast these percolation waves propagate through an iron aerosol cloud? And then as a function of particle size distribution and particle density. Just to, some viewers might already have noted the length scale in this image. So this is 1 centimeter. This simulation was 1 centimeter cubed of volume. For this experiment, it already contained over 4 million particles. So this already illustrates the difficulty with resolving all these very small particles. The number of particles gets really, really, really large quickly. So for industrial problems, we need to find better solutions because they are intractable. We would like to resolve all particles. Because that's what we would like to do. We would like to scale it up. So the next step here is the 3 kilowatt burner initially developed by Tim Spey. It's currently being operated by Mohamed Reza and being developed to also to be able to run under mild conditions. it injects a stream of iron powder from the top, which is swirled by two small air injectors, which can be seen here. And you get this rotating vortex containing burning iron particles. We are still studying the exact behavior of this burner because it's still, we do not fully understand the stabilization mechanisms of this burner. And for this purpose, we also use the code to simulate it and to see if we can reproduce the observed behavior in the experiments. This is work in progress. And this is to show that we are really scaling up to kilowatt scale. To give you an indication of the CPU hours for this simulation, it took about, am I correct? 50,000 CPU hours. So that illustrates that it gets quite expensive quickly for even kilowatt scale burners. Because this is the goal. So this is the old MP100, 100 kilowatt scale burner, which is currently being redesigned, built and tested to operate under even higher loads. So we're talking about 200 and 500 kilowatt thermal power loading. And the previous simulations and the associated numerical cost already illustrate that we need to come up with smart solutions to be able to use numerical tools to design and optimize these kind of burners. So in short, the metal fuel cycle is a promising way of storing, especially carbon-free energy. So it is a good way to store this energy, which is originating from green sources like wind and solar electricity. It needs to be noted here that it has most potential for stationary applications, so large-scale stationary applications. And this would make it especially interesting also to retrofit coal power plants and to keep on using them over the next decades without using any coal. From all metals that have been considered, iron is the most promising metal fuel. And the most important reason for this is that it produces very limited amount of gaseous oxides and nanoparticles. So that makes it, first of all, an easy fuel to recycle because we can capture all the oxides as particles. And second of all, these nanoparticles that are formed using other metals, there are strong indications that they can be harmful for human beings. So we do not want to emit these nanoparticles. So that makes iron the most promising metal fuel that has been found so far. And to be able to develop this iron fuel, first of all, we need to do accurate measurements. At the moment, these measurements are very hard. But we need these experiments to validate also our tools, which in turn can be used to design the required equipment. Here in Eindhoven, we are conducting these experiments from small scale, so single particles, all the way to lab scale burners, kilowatt burners. And we're incorporating an extensive measurement procedure to characterize these unburnt and burnt particles. This measurement procedure contains particle size analysis, electron microscope to visualize actually the particles to characterize their morphology, but also X-ray diffraction to characterize their exact composition. So especially when they're burnt, we would like to know which oxides have been formed. In parallel to these experiments, several numerical tools are being developed, and we have tools with increasing complexity. We have unresolved single particle models, which run fast and are fairly accurate. and we have very accurate models for resolved single particle simulations, resolved one-dimensional flames, and also large aerosol flames. But we need to validate these numerical tools in order to be able to use them to steer combustor development. So in the end, development of the equipment that needs to be developed to be able to run this technology, to be able to use it. So this brings me to the end of the my presentation. So first of all, I would like to stress this is not my work. My work is only a very small part of it. There is an enormous amount of effort and enormous list of people who have been involved in this and work very hard on this subject. So with this, I would just like to list them. If you have any questions concerning a specific topic that has been touched today, please contact me and I'll put you in contact with the person who is actually conducting this research. Thank you very much for your attention. I'm looking forward to your questions.